Welcome to this lecture of my series on advanced mathematical physics, in which we are currently discussing differential geometry. Today's lecture will be essentially on one notion, that of a push forward of vector fields. But in order to discuss this, we need to first talk about push forwards of a tangent vector. And let me just remind you that in order to get to the notion of a push forward of a tangent vector, we must first figure out what exactly the pullback of a function. So just a reminder, given a smooth map psi from a manifold M to a manifold N, the pullback of a function written psi with an upper star, so this is pullback induced by the map psi, is a way of mapping C infinity n, the set of all smooth functions on n, to C infinity m. The way this works is the following. You take a function f from C infinity n, a smooth function on n, and you map that to psi upper star f, a function of C infinity m. And the definition of psi star f is simply, it's f composed with psi. You first apply psi to take a point on the manifold M to a point on the manifold N, and there you apply the function f to get a real number. So this, of course, is a function from the manifold M to the set of real numbers, and if the map psi is a smooth map, it is easy to show that f composite psi will be a smooth function, given that f is, of course, f being a member of C infinity n is known to be a smooth function. This just guarantees that psi star is a map from C infinity n to C infinity m. Now, using this notion of a pullback of a function, we can then define what a push forward of a vector, a tangent vector, is. Now, since tangent vectors to a manifold are stuck to points on the manifold, the push forward actually is also characterized by the point you're talking about. So given the same structure, that is, given a smooth map psi from M to N, you define psi star P. This is a map, psi star P. Here, notice star is written downstairs and the point P is being mentioned. This is a map whose domain is TPM, the tangent plane to the manifold M at the point P, and whose range is T psi PM, the tangent plane to the manifold M at the point psi P. Now, given a vector Vp belonging to TPM, psi star P Vp, that is, the vector which psi star P maps Vp into, is a member of T psi Pn, as we have just said, and the way in which this psi star P Vp is defined is the following. Given a smooth function f belonging to C infinity n, psi star P Vp's action on f, the value which the functional psi star P Vp takes when given the function f as an argument, is defined to be the result of Vp acting on the pullback function psi star f. So basically, what you do is, given a function f on the manifold n, you pull it back to the manifold m and you apply Vp on that. And we have discussed in earlier lectures why doing this to Vp gives you a valid tangent vector at the point psi p of n. Now the question that we have is the following. If you have a vector field defined on a manifold M, that is, a map which maps points on M to tangent vectors tied to those points, can we actually push this vector field from M using this map psi to the manifold N? Before we answer that, just a quick reminder about the terminology. This map psi star P is also called the Jacobian of the map psi at the point P. So, while the Jacobian map allows us to push tangent vectors from one manifold to another, the answer to the question about can vector field be pushed forward may not always be positive. This method of pushing vectors from one manifold to another may not really work well with vector fields. Why? The answer is sort of obvious. This map psi from M to N is smooth and differentiable, that's fine, but it is not guaranteed to be injective a priori. So, in such a situation, what might happen is that there may be two different points P and Q on M such that P is not equal to Q, but they map onto the same point under psi. That is, psi of P is the same as psi of Q. Now, it's very possible that if you have a vector field x on M, it will take a value xp at the point P and a value xq at the point Q. But when you try pushing forward xp and xq respectively using psi star P and psi star Q, the resulting vector, both of which are actually vectors at the point psi P. Remember, psi P and psi Q are the same. The resulting vectors may not match. So now you have a problem as to which one of them should you really call the value of the pushed forward vector field at the point psi of P. Because of this ambiguity, it is not in general possible to push forward vector fields from one manifold to another, although it is possible to push vectors forward from each point on the manifold M to the target points on the manifold N. Now, there are, however, special cases when this approach can actually work. Now, one such special case is, of course, when the map psi is 1 to 1 and there is no possibility of psi of P being equal to psi of Q if P and Q are different. Then this problem goes away. Let me point out, however, that it is possible that even if the map psi is not injective, it so turns out that psi star P xp is the same as psi star Q xq for some specific vector field. And if that happens, that vector field can also be thought of as being pushed forward using the map psi to yield a new vector field. Now, more generally, if X is a vector field on M, a smooth vector field, a member of fracture Xm, and Y is a smooth vector field on N, then we say that X and Y are psi-related, which is another way of saying Y is what you get when you push forward X point by point using psi. If the following happens, if for all P belonging to the manifold M, if you push forward xp using psi star P, you do get Y at psi. In such a case, you can really be justified in saying that you have pushed the vector field X forward onto the manifold N and it has given you the vector field Y on N. The terminology is really not pushed forward for the simple reason that this method does not work for all vector fields for reasons that we have just explained. So the standard terminology that is used is X and Y are psi-related if this happens. Now, if this is true, then it is easy to see the following. If we take any function f in C infinity n, that is a smooth function on the manifold n, and apply y, the vector field, in its function to function operator avatar on the function f, the value of yf at the point psi p, which by definition is the number yielded by the action of y psi p, the tangent vector at the point psi p, eating up the function f. Now, by definition, y psi p is psi star p xp, so there is psi star p xp acting on f. But by the definition of push forward of a vector field, psi star p xp acting on f is the same as xp acting on the pullback of the function psi star f. In other words, it's xp acting on f composite psi, and therefore it's x acting on the function f composite psi at the point P. Now, putting all of this together, what you see is x, the vector field on M, acting on the pulled back function f composite psi, yields a function whose value at the point P is the same as yf composite psi at the point P. In other words, yf composed with psi is the same as x acting on f composite psi. So when x and y two vector fields are psi-related, then for every smooth function f on N, you have this very interesting result, that the result of acting y on f and then composing this with psi, of course you let psi act first, then you let yf act after that, is the same as letting f compose with psi first to produce the pullback function and then applying the vector field on it. So in other words, what you are really saying is yf is a function on the manifold N which you are pulling back using psi. And the resulting thing is the same as x acting on the pullback function. In other words, pullback psi star of yf is the same as x acting on psi star f. In a sense, if x and y are psi-related, then essentially the actions commute in this very sense. You can apply x after pulling back with psi, or you can first apply y and then pull it back, and you get the same resulting function in both cases. Now we will have plenty of occasion to use this idea of two vector fields on two different manifolds, or perhaps even the same manifold, being psi-related. At this point, this idea may seem a bit abstract, so what I will do in the rest of this lecture is talk about a specific example of a vector field which is psi-related to another one, in the hope that this will make the things a bit clearer. Now here, the map psi that we are going to talk about is a map from a disk D, the set of all points xy in a plane such that x square plus y square is less than 1, from D to R3, the standard three-dimensional Euclidean space. Now, in order to specify the particular differential map psi that we are talking about, we could have told you what psi does to every point on D, but it's actually equivalent to specify the pullback functions of x, y and z, the coordinate functions of R3 pulled back by psi. If you specify all three, a moment's thought would essentially tell you that this will give us enough information to reconstruct the function psi. Pullback here is given by these functions. Psi star x is 2x by 1 minus x square minus y square. Psi star y is 2y by 1 minus x square plus y minus y square. Psi star z is 1 plus x square plus y square by 1 minus x square minus y square. As you will find in a later application, this particular map is not really a very arbitrary one. It's quite useful, as you will see in a later context. But for the time being, this is just some map which essentially is telling me that if you were to take a point xy on D and map that using psi, the small x, small y, small z coordinates of the mapped point are going to be this, this and this respectively. So this is essentially how we talk about maps. We don't really talk about abstract points on N going to some abstract point on N. We essentially talk about coordinates of the point M leading to the point itself and then mapping onto another point on N whose coordinates are given. So it's really a coordinate to coordinate map that we are used to specifying. And that's exactly what this is. This gives us the small x, small y, small z coordinates, the three coordinates on psi using the standard chart on R3. And this is what we are going to do here. We have a vector field on D which is defined to be V given by half of 1 minus x square plus y square del del x minus xy del del y Again, this is vector field will turn out to be quite useful in the later application, but for the time being, it's just a vector field on D. And I have called it V rather than X for obvious reasons. Capital X is actually being used as a coordinate on D, and I don't want you to get the two mixed up. So we have V, which is given by this. We have specified V by specifying it in its differential operator avatar. Essentially, we have said that the components of V in the coordinate basis given by del del x and del del y are half of 1 minus x square plus y square and minus xy respectively. Now, if you take a point P on the disk D, psi star P Vp has to be a tangent vector to R3 at the point psi P. So, this is a member of T psi P R3. The components of psi star P Vp with respect to the standard basis that the coordinates give you on R3, that is del del x, del del y, del del z, at the point psi P, are what you really need to completely specify the vector field psi star P Vp, and these components are, according to the definition of this psi-relatedness, psi star P Vp acting on x, psi star P Vp acting on y, and psi star P Vp acting on z respectively. So let us take a look at each of the three components in succession. So what is psi star P Vp acting on x? By definition, it's nothing but Vp acting on the pulled back function psi star x, and that is the same as V, the vector field acting on the pulled back function psi star x, leading to a new function being evaluated at the point. That's essentially what Vp acting on psi star x is defined to be, or rather, that's basically what this function, the vector field acting on another function, is defined via. So we have just used that. Now V in our capital X, capital Y coordinates is simply given by this, and psi star x, the pulled back function, is basically this. So what you have to do is apply this vector field on this function and figure out its value at the point P. And that's pretty straightforward. We have already discussed before that although these are actually not exactly partial derivatives, in terms of the proxy functions, they do really work like partial derivatives. So, half into 1 minus x square plus y square, this cofactor, times del del x of this. So, we have calculated the partial derivative here, and we've partially calculated it using the standard formula for a derivative of ratios. And in addition to that, you have minus xy times the partial derivative of this. I've actually compensated for the minus sign already, because there will be a minus sign coming in from this calculation. So you've got a plus there. Now if you put all of these together, do some algebra. It's just plain algebra, although the algebra may be slightly time consuming. Calculate it all out, you end up with finally this expression. The value of 1 plus x square plus y square by 1 minus x square minus y square evaluated at the point P. Notice that this is nothing but psi star z evaluated at the point P. After all, we need to rewrite everything in terms of x, y, z. So this is again z at the point psi P. That's what psi star z at per point P is. Of course, that's what it is. It is the z value of the image point. So, the first component, psi star P Vp acting on x, is simply z at the point psi P. We can carry this on. We will calculate psi star P Vp acting on y, which by definition is Vp acting on the pullback psi star y. That by definition of the vector field V acting on a function is V acting on psi star y evaluated at P. We replace V by its coordinate differential version, psi star y in terms of the coordinates. Carry out the partial derivative, do a bit of algebra. I urge you to carry out the algebra yourself to check that what I am saying is right. But once you carry out the entire algebra, you will see that you get a 0. So there is no del y component of psi star PVP in this case. What about the z component? For that, you have to evaluate psi star PVP acting on z, VP acting on the pulled back function psi star z, or, which is the same thing, V acting on the function psi star z evaluated at the point P. And in this version, we actually do the calculation in a pretty straightforward manner. We just plug in V and psi star z, carry out the derivative. Again, takes quite a lot of algebra to work this out. But once you work this out, you actually end up with a lot of cancellation. So it's not really as bad as it looks. You finally end up with twice x by 1 minus x square minus y square evaluated at the point P. But notice that this is nothing but psi star x at the point P, or the x coordinate at the point psi P. Tangent vector psi star PVP 2r3 at the point psi P has components which are nothing but z at psi P and x at psi P for the x and z components respectively, and no y component. So the expression that you can write down is z at psi P del x at psi P plus x at psi P del z at psi P. Let me just remind you that when you take a vector field A and multiply that by a function f, the value of that resulting vector field at the point P is defined to be f of p a p, or equivalently f of p times a sub p, which is nothing but a, the vector field at the point P. So using that in reverse, we can easily rewrite this as the vector field z del x plus x del z evaluated at the point psi P. So our vector field V that was defined on D is actually psi-related to z del x plus x del z on R3. Now it turns out that this vector field z del x plus x del z, along with a set of other similar vector fields, has important mathematical and physics applications. And that is why this particular problem is not just of academic interest, it's actually quite a useful vector field, and it's important to figure out what vector field on a disk is psi-related to. The application will come later, but for the time being, I hope this example has made the idea of two vector fields being psi-related a bit clearer. I would urge all of you to take down pen and paper. This is not really spectator sport. You cannot really just listen to a lecture and understand what's going on. You should actually carry out the steps that I had indicated above and convince yourself that the algebra that you carry out really gives you z and x, rather z0 and x as the three components. Now my original plan was to stop this particular lecture here and come back to the issue of psi-relatedness in later lectures as and when we need to talk about it. However, this particular example that we talked about right now may seem a bit artificial to you at present because you have not really seen the context in which this particular vector field would be useful. However, what we can talk about at this point is a very, very important example of two vector fields being psi-related, where the importance of those vector fields is something that no one would dispute. So at least let me give you that example to begin with. And after that, I'm also going to continue by showing you how this relationship of being psi-related between vector fields actually plays rather nicely with an operation that we studied over the last couple of lectures. That is the Lie bracket. But first, this example. For this example, we need a map between two manifolds, of course, the map which is going to play the role of psi in our description. And this map is nothing but the projection pi, because the two manifolds that we are talking about are Tm, the tangent bundle to the manifold M, and M itself. Let me just remind you that every element of Tm is a tangent vector to the manifold M, and of course a tangent vector Vp must belong to Tpm for some particular P. That is, must be in one tangent plane of the manifold or the other. And what the projection map does is that when it's applied to this vector Vp, the element of Tm, you get the point P, the point at which the vector is back. Now, if you have a chart u comma phi on M, we have written chart phi, but that really means the map. The coordinate map is phi. This induces 1 on Tm. And how is this done? The answer is simple. Remember, any chart or coordinate system that you introduce on Tm should at least take all the elements in some open set of Tm, the u bar, the domain of this new chart, u bar comma phi bar, and figure out what its coordinates are. Now for this, let me point out that Vp, these vectors, can automatically be completely described if you tell me what its components are according to some basis, as well as the point P where the Vp is tangent to the manifold. Now the point P is easily written down in terms of the coordinates provided by the chart u comma phi. And actually, this phi applied to P will give you these coordinates x1, p, x2, p up to xn, p, the n coordinates for the point, and that will be part of the description of Vp. Where do you have this vector stuck? On the other hand, these coordinates also immediately give us a choice for basis, the del xip basis vectors that we have talked about. So Vp can be described completely given this basis del xip by providing the components, which are nothing but the result of Vp acting on the functions xi, the ith coordinate functions. And it is these numbers, which are now actually 2n in number, n for these coordinates and n Vp xi's, which actually give us the coordinates for Vp in this induced chart. So, the ith coordinate for the point P, xip, stands for one particular kind of coordinate, the kind that we call qi of Vp. Of course, we are using qi, as we have said earlier, because we are using an analogy with classical mechanics here. And to continue that analogy, the components of the velocity vector Vp xi is actually written q dot I of Vp. So the chart u bar comma phi bar has this map. Phi bar of Vp is given by a bunch of 2n numbers, the first n of which are actually the coordinates of the point P, but we are writing them as q1 Vp up to qn Vp. Followed by that, you have n components of the vector Vp in the basis provided by del xip. So these are really what those numbers are. Now, this is again old stuff, but I'm just recapitulating this for your benefit now. Qi acting on Vp is nothing but xip, so that's xi. It's the projection pi of Vp. So that's xi composite pi acting on Vp, and hence qi, these functions are nothing but xi composite pi, or basically the pullback of the functions xi using the pullback map induced by pi. So pi maps Tm to M, and pi star, this pullback map, pulls functions from M back to Tm. And the most obvious example of that is the coordinate functions on M are pulled back to give you the first n parts of the coordinate function on Tm. Now, given the fact that you have qi's as coordinate functions, you automatically will get del qi at the point V, where V is some point in Tm, some tangent vector. And how do you apply the push forward operation pi star V on that? Well, in order to see what comes out of this, you have to give this a function f to act upon. Remember, this function f has to be a smooth function on M, a member of C infinity M, because this pi star v del del qi v should give you a vector on M. So what is this vector? Well, by definition, this is del del qi of v eating up the pullback of f, pi star f, or f composite pi, which is of course the same thing. Now, in order to see exactly what this is, I'm pretty sure many of you can immediately tell me what this is without any further calculation, but if you want to see this explicitly, this is what the result really is. You have to fall back upon the definition of these del del qi v's. Remember, this is actually a coordinate basis vector, and by definition, whenever you use a coordinate basis vector, I'm writing this as del del xi in general for any manifold. When this acts on some function f, the result actually is limit as t goes to 0 of f composite phi inverse, the proxy function, evaluated at the coordinates of the point where you're actually evaluating this. This is of course at some point p. So these are not really x1, x2, xn the functions. I'm just writing them in short. These are x1, p, x2, p, xn, p. But what you must remember to do is change xi p to xi plus t. Subtract the original f composite phi inverse, the proxy function, at the original value from there. Divide this by t. In other words, you're actually finding out the derivative at t equal to 0 of the proxy function. So here we do the same thing. Our function is f composite pi. So what we should do is take the proxy function of that, f composite pi composite phi bar inverse, and figure out how much this function changes when you change the ith coordinate, here qi, from the value qiv to the value qiv plus t. Everything else staying the same. And notice that this whole thing, f composite pi composite phi bar inverse, is nothing but f composite phi inverse, the proxy function on the manifold, composed with phi composite pi composite phi bar inverse. Now what does this phi composite pi composite phi bar inverse actually do? Phi bar inverse acts on the components of a tangent vector which has two n numbers and gives you back the original vector. Pi just gives you the point where that vector is attached. And what does phi do? It gives you the coordinates of that point. So phi composite pi composite phi bar inverse simply takes the two n numbers which were components of the vector v, or coordinates for the vector v, on the tangent bundle, and then simply drops the vector components and gives you the first n coordinates. So basically what you are doing here is applying the proxy function f composite phi inverse on the first n components, or just the n coordinates, x1, x2 up to xn. And therefore, this thing is actually nothing but the value of f composite phi inverse evaluated at xi of pi v plus t minus the value of the same function evaluated at xi of pi v, all the other coordinates being the same as those of pi v, the point where the vector is stuck. You divide the difference by t and take the limit as t goes to 0, and that is nothing but our definition of del del xi of pi v eating up f. So pi star v del del qi v acting on f is nothing but del del xi. Pi v acting on f, and since this works for all f, this is the general result between the coordinate basis vectors. If you push forward the coordinate basis vectors using the projection operation from the tangent manifold, you actually end up with the coordinate basis vectors at the point on the manifold which pi is projecting onto. And this actually means that if you look at the vector fields del del qi, whose value at the point v is del del qi v sitting here, and the coordinate basis vector fields on the manifold M, del del xi, these are pi-related. And just from what we had learned a while ago, this will also tell us that for any function f on the manifold, you can apply del del xj on that to get a new function on the manifold and pull it back using pi star to Tm, the tangent bundle. The result is the same as pulling the function f back using pi star first to the tangent bundle and then applying del del qi on that. Let me end today's lecture with this very important result that I talked about earlier, the connection between psi-relatedness and Lie brackets. For this, let us start with this basic setup. Psi is a map from M to N. x1 and x2 are smooth vector fields on M, and they are psi-related to y1 and y2, which are smooth vector fields on N respectively. So for any f which belongs to the set of smooth maps on N, the following works. Pulling back the result of y1 acting on f, y1f composite psi, is the same as x1 acting on the pulled back function f composite psi. And similarly, pulling back y2f to M is the same as x2 acting on the pulled back function f composite psi. Now what about the Lie brackets? Well, for this, let us take a look at what happens when you try pulling back the Lie bracket y1, y2 acting on the function f. Remember, f is a function on C infinity n, and y1 and y2 are of course smooth vector fields on n. By definition of the Lie bracket, this is y1 acting on y2f minus y2 acting on y1f. Of course, this whole thing is composed by psi, that is pulled back to M. Now, you can break this up into two very simple pieces. This is an obvious property of the pullback. Is y1, y2f composite psi minus y2, y1f composite psi. Now let's take a look at this. y1, y2f composite psi. y2f is some function on N. So this is y1 acting on some function of N pulled back. Remember, y1 acting on any function f pulled back is basically x1 acting on the pullback of that function. So y1 acting on y2f pulled back by composing this psi is nothing but x1 acting on y2 acting on f pulled back with psi. It is nothing but this result which has been used. And similarly, y2 acting on y1f, this function pulled back using psi is nothing but x2 acting on y1f pulled back using psi. But then in the next step, y2f pulled back using psi, y2f composite psi is nothing but x2 acting on f composite psi, and similarly here you have x1 acting on f composite psi. As a result, what you end up with is x1, x2 Lie bracket acts on f composite psi. So, y1, y2's Lie bracket acting on f pulled back with psi for any smooth function f on N is the same as pulling back using psi, this function f, and then applying the Lie bracket of x1, x2 on it. And this tells us that the Lie bracket x1, x2 is psi-related to the Lie bracket of y1 and y2. So at the end of it, what we see is Lie brackets actually work very well with the notion of psi-relatedness. If x1 and x2 are psi-related to y1 and y2, the Lie bracket of x1 and x2 is psi-related to the Lie bracket of y1 and y2. This result is also going to be pretty useful later on when we talk about Lie brackets a lot more. Now we will see other features of this so-called push-forward operation later on, but for the time being, let me just end this today. In the next lecture, we are going to introduce a very, very important entity, the differential form or one form. Bye till then.